And finally, this is the last part. This is the last short lecture in this topic, in this chapter, which is number 10. So I'm going to solve the last example. So still, this is chapter 1, Introduction, Basic Concepts. So this is example 4 that I'm going to discuss, which will conclude this chapter. So a forklift raises a 90.5 kilogram crate. So this is a forklift, as you can see, and it raises a 90.5 kilograms crate. So this is the crate. Let us say it weighs 90 kilograms, and it raises it for 1.8 meters. So this is from here to there is 1.8. Okay, from the ground up 1.8 meters. So what do we have here? We have the mass of the crate, m is equal to 90.5 kilograms, and we have the distance, let us say distance, that this crate was moved. So I will just call it d if you want, is equal to 1.8 meters. This is the only thing that we have. Showing all your work using unity conversion ratios, calculate the work done by the forklift in units of kilojoule. So now I want the work in kilojoules. Okay, showing all your work using unity conversion ratios. Calculate the work done by the forklift in the units of kilojoules. So how to do this? How to do this? We have to think, as I said. You have also to think about the what did we say about the using sense of the units, how to deal with them, how to multiply them or to get whatever we want. So at the end of the day, then I want the work, and the unit of the work is in joules or kilojoules. And you know that joule is equal to Newton times meter. This is how we think about it. I've got the meter here, which is the distance that was raised by this forklift, but I am in need for a force, which is got the unit of Newton. So I have the mass of the crate, which is 90.5 kilograms. So you know what I can get out of the mass in terms of a force, which is the weight. So then I can use the mass to get the weight of the crate, which is a force. And then if I multiply this force by the height, I'm going to get joules, which is the work that this forklift has to put in order for this crate to be raised. This is how we analyze it. Okay, this is how we analyze the problem. And then the next step, if it takes 12.3 seconds to lift the crate, calculate the useful power supplied to the crate in kilowatts. So this is one part, which is the work, and then he's asking for the power. So we know that the power is measured in watts, okay, watts or kilowatts, and we know that a watt is equal to joule per second. So if I got the joules here from part A, if I divide by the time, which is here, it is given in part B, so joule per second will give me watts. And then I can calculate the useful power supplied to the crate in kilowatts. So this is how you analyze the problem. Whatever you got, you think about the, let us say, how to deal with the numbers. Shall you multiply them, divide them, as you can see, we have done in this problem. So let us see the solution. Okay, so the solution, we are to estimate the work and power required. This is what's required. Assumptions, the vertical speed of the crate is constant, so the speed is not changing. And the properties, we have the gravitational constant to be 9.807, the acceleration due to gravity. And as I told you, so for the work, we'll take the mass, multiply it by g, so this will give us the weight, which is the force in this case. We multiply it by the delta z, the distance the crate was, let us say, raised. And from now on, you can use the conversion factors. So This is between for the force, and this is for the work. Let me show you the conversion table for the last time. So what we have here, we have the you know that 1 Newton is equal 1 kilogram times meter per second square. So this is for the force. And then for the energy or the work, you know that 1 kilojoule is equal to 1000 Newton meter. So we'll use these two. We'll use the force and we'll use the energy. So this is what we will use from this table. Okay, so I'm back. So this is what we said. This is mass. Now mass times acceleration is force or weight times delta z. This will give me uh, the work. And now those are unity conversion factors. And at the end of the day, I got this, which is 1.6 kilojoule of, of work. Okay, 1.6 kilojoule of work. Um, uh, so I will leave the comment on you. Look at your book. So I believe there is in your book, there is something that you can relate it to this. I mean, is it a lot? Is it small quantity? So I want you to go to your book, and I believe that there is an example about this, about the joules or calories, etc. So I will keep this for you. Now, for the second part, which is for the power, so all what you have to do, as we did, as I told you, so we'll take the work, which is 1.6 kilojoule. I will divide it by the time, and I'm going to use this unity conversion factor, which is for power. Let me go to my slide there. Okay, so power, this is power, which is, I believe, 1 watt is equal to here, 1 watt is equal to 1 joule per second, 1 kilowatt is equal 1000 watts. So this is what you need. So in the first part, we use the energy and I believe the force, and now we are using the power conversion. This is how you will use your table. Okay, and finally, so you will do this. Sorry for that. So as I said, you will do this, and finally we'll get around 130 watt. Again, you have to comment on this. 130 watt. This is the power needed, which is not much. It is like the power needed to, to power 3 light bulbs. But not energy savers. Energy saver even will utilize less power. I'm talking about regular light bulbs, fluorescent lights. Fluorescent is the long one, right? Semi-fluorescent. So as I said, when you get the number, the final answer, you have to be able to comment. How to comment to say if, if to say if it makes sense or not. And then if it makes sense, you have to compare it with something that you know. And we are building on our knowledge in this regard. Thank you very much. This ends this chapter. I have just, this is the 10th lecture. I have solved 4 examples. I discuss a lot of stuff. And the door will be open for your questions in the tutorial